we're going to introduce the idea of hypothesis testing, which we will build up to do t-tests, both a one sample and a two sample t-test. We'll introduce the idea of the p-value, finding statistical significance with the p-value. And this will set the framework or the base for you to learn all sorts of statistical tests to answer all types of research questions. Hypothesis testing is sort of the flip side of estimation. It's really the same thing. The way hypothesis testing works is it's a statement of belief about some population parameter. You explicitly state, I think blank is true. And this is what we're going to call the null hypothesis, or the H naught, or the H sub 0. The null hypothesis is a statement of belief about a parameter. So here's our parameter, mu, which is the population mean. And you say, I believe that the average Frisbee holds, right, is equal to 72 ounces. Now, where did this come from, this statement of belief? Oh, Tibor told me. He said he heard it once on an ultimate Frisbee field. So these can come from anywhere, right? The average person should consume 30% of their calories from fat. Where did that come from? The average person has 99 problems. Where did that come from, right? It's a statement of belief. But as long as we state it explicitly, then we can test it. Now, remember, the null hypothesis is usually something that we want to knock down or disprove, right? So here's how this works. We state the null hypothesis. Oh, look, it's really good. All right, it doesn't want to delete. We state the null hypothesis, and then we also state the alternative hypothesis. And the alternative is literally simply not the null. So if the null hypothesis is that you can fit 6 beers into a Frisbee, 72 ounces, then the alternative would be, hey, you can't, right? Not the null. So let's think through this. This is what's known as a one sample t-test, because we're just taking a sample of things, calculating the mean, and then saying, what does this tell us about the mean of that sample? So one sample t-test. State your null hypothesis, and then you go out and collect some data. With that data, you calculate what's called a t-statistic. Remember what a statistic is. A statistic is just a number that describes your sample. It's a number that describes your sample. And we're going to do a statistic, which is called the t-statistic. And here's how you calculate it. You take your mean, and you see how far away it is from that hypothesized mean or that null value. So X bar, and you see the difference from the null hypothesis. You can think of it as sort of like the signal or the strength of something that's trying to come through. And then you divide it by, oh, look at this, standard deviation over the square root of n. What's that? That looks familiar to me. This whole thing actually looks familiar to me, this whole equation. This whole equation, to me, it kind of looks like a z-score. Remember, a z-score was each value minus the mean divided by the standard deviation. So we said a z-score is how many standard deviations am I from the mean? This, if you recognize that this is the SEM, then the t-statistic is how many SEMs is my mean. What do you mean by my mean? Well, I mean X bar, the mean that you got, right? How many SEMs is my mean from the null hypothesis? How many SEMs is my mean from the null hypothesis? If it's a lot of SEMs, it's really far away, then it's weird, right? Remember, if somebody says, hey, your z-score is 5, you don't need to know anything else. You're like, wow, 5 is pretty weird. That's pretty far away from the mean. It's the same sort of deal here. If your SEM is really big, you're like, well, that's pretty weird. I wouldn't expect to see that under the null hypothesis. So we have to really think through of what would we get if the null hypothesis is true, right? What would we see if the null hypothesis is true? That's our distribution or our background or our baseline. And then we're going to take our data and we're going to plot it on top or reference it in the distribution if the null was true. So we set this null hypothesis. We're going to think through what the distribution of that statistic would look like if the null is true. And then we're going to just say, well, let's see what we got compared to what we would expect to get. And if it's really weird, maybe we can evaluate that null hypothesis. If it's really, really weird, maybe that null hypothesis should be rejected. If it's not that weird, then maybe we failed to reject it. And this is the idea of taking your statistic, you turn it into what's called the p-value, which we'll see in a minute, and then you look at that p-value relative to your criterion for weirdness, which we already saw, called the alpha level. So let's walk through this in a little more detail. Again, with the Frisbees. So someone tells me that you can fit a 6-pack of beer into this Frisbee. All right, I go out and I collect some data. Let's say I get a sample mean of this. Let's say the standard error is this. I already have my null hypothesis. That's what Tibor told me, 72 ounces, a 6-pack of beer. So now I get a one-number summary of my data, a one-number summary, my statistic, and it's called T. And again, the numerator of T, I'll write it out like this. T equals your mean minus this hypothesized mean, which is 72 ounces. Now, maybe in Australia, when they play Ultimate Frisbee, they measure beer in different sorts of ounces, or maybe the Brits or the Germans or the Belgians, they do it differently. But here we say it's a 6-pack, 12 ounces, 72. So that is our signal. And then we have to divide it by the inherent variability that we would expect anyway. What do I mean by that? Well, think about it for a second. If a Frisbee actually could fit 6 beers, and you got a bunch of Frisbees and calculated the average, do you think that average would actually be exactly 72.00000? No, that would be weird. There's going to be some random variability. How much variability would there be? How much would that mean bounce around? I know that. That's what the SEM is. It quantifies how much random variability there is by chance. So the T statistic really does summarize how many SEMs is my mean from that hypothesized mean. And in this case, we see that it's 10. Now, what does that mean? Can we turn that 10 into something that's meaningful? Yeah. Well, we say, what would we expect to get if the null hypothesis were true? Well, remember, T is your mean minus the hypothesized mean divided by, I'll just write SEM here, SEM. So what would you expect to get if the null hypothesis were true? Well, you would expect to get something here around 72. And your null hypothesis is 72. So 72 minus 72 is 0. You would expect to get something around 0. And if you did this again and again and again, see I have over here, over and over and over again, you would get a distribution of T statistics that's centered around 0. Now, sometimes it would be a little bit higher, and sometimes it would be a little bit lower. How much would it bounce around due to chance? That's the SEM. That's what the number summarizes. So 68% of the time, it would be within 1 SEM. 95% of the time, it would be in 2 SEM, and so on. That's what the T statistic is. It's how many SEMs is my mean away from the population mean. So this graph, this graph is what you would expect to see if the null was true. Now, what we're going to do is say, what's the probability of getting my data if the null were true? And remember what we got for this example. We got T equals 10.49. I think that's what it is. Antonio, edit that back out if that's the wrong number. T equals 10.49. So in other words, I got to go on this curve, and I got to go 4, 5, 6, 7. I literally got to go off the charts here to see where 10.49 is. Here is 10.49. So we put that T statistic, the one number summary of our data, we put it on the distribution if the null were true, is way out there. Stata or your software will look it up for you. And the area to the right of this, very small. And this is what's known as the p-value. The probability of observing a test statistic of a given magnitude or larger if the null hypothesis is true. So work that out backward. If the null hypothesis is true, well, if the null were true, I would expect to get something around 0. Remember, t equals x bar minus the null hypothesis divided by SEM. If it were true, I would expect to get 0. So that's what this curve is, if it were true. And then I say the probability of observing a test statistic, that's t, of a given value, 10.49, what I got, or larger, that's the area to the right. And I just color in that area. Now, we actually do what's called a two-sided test. So in addition to going to positive 10.49, we go to the other side. We go to negative 10.49, and we look over there too. And we look at those two sides. How much did we color in? What percent of the curve? A very, very tiny amount. And that's called the p-value. We'll talk about what we do with that p-value in terms of statistical significance next.